All right, let's look at an example of type 2. So in this case, we have a fixed upper bound and our lower bound is negative infinity. So remember what that does to us. We again create a definite integral with an upper bound as our sort of finite fixed upper bound from the original problem, and our lower bound is our new dummy variable, which we've been calling b. But in this case, b is going to negative infinity instead of positive infinity, and we're going to talk about how that changes. So the first example we have here is we're taking the improper integral from negative infinity to 0 of e to the x. And let's remember what the function y equals e to the x looks like. So maybe I'll draw it over here. Remember, this is just the exponential function. So crosses at 1, goes up pretty quickly. Probably quicker than that. Not a great picture, but we will move on. And so if we're looking at this integral, the area we're talking about starts at 0, but it doesn't go this way. It goes backwards, right? It goes to negative infinity, and so negative infinity somewhere out there. So we're starting from 0, and notice that our exponential function does get lower as we go to the left, so we do have a chance here of actually having a finite answer. Okay, so let's see if we do. Let's apply the rule here, which is using the limit definition. Okay, so let's take the limit as b goes to negative infinity. Our a in this example is 0, and we're going to call this b and go e to the x dx. Okay, so again, the first part of this is just like any definite integral. We're going to take the antiderivative. In this case, what's the antiderivative of e to the x? It's the only function that doesn't change. Well, it is a function that doesn't change when we take the integral. So we get something like this, right? And we can plug these in. So we get e to the 0 minus e to the b. And we'll go ahead and we can simplify e to the 0. So let's go ahead and say what that is. It's just the number 1 and then e to the b. Okay, so we're taking the limit with respect to b. So the 1 is a constant, doesn't change at all. And there's a couple of things we can do here. So we can either sort of, by inspection and maybe just sort of common sense, think about what should happen as b goes to negative infinity. If it's in the exponent of e is a positive number being raised to a power. If I raise it to a negative power, it's going to be 1 over that. So we're going to get a fraction. And the fraction we're going to get. So and another way to think about this too is that this is going to be the limit as b goes to infinity if I change this to negative b. So the limit as b goes to negative infinity is the same of a function of b is the same as the limit of b going to infinity of a function of negative b. So I can sort of switch all the b's to negative and switch that to positive. Because if b is going to negative infinity, then negative b is certainly going to the same place. I mean, e to the negative b is certainly going to the same place when b goes to infinity. Okay, so what does this look like then? Well, then you have the limit as b goes to infinity of 1 minus 1 over e to the b. And when b is going to infinity, e is a positive number greater than 1, so this number is just getting larger and larger, of course, and so this thing is going to 0, right? And 1 is constant in this case, so we just get 1. And so this is the area under this curve on this side. Going all the way out to infinity is just going to be 1.